I wanted to make a few notes about what I said in the last video, which was the keys behind sampling distribution, which is the key, which was the idea that the larger the sample, the more accurate it will be in general. And one of the important conclusions about the standard deviation is that the standard deviation for a larger sample will be smaller because in general it is more accurate. There's less variation in the distribution. It will be more closely clustered towards the actual mean. And the fact that the standard deviation is smaller means that it will actually affect the pattern of the normal distribution. And also, kind of another important thing about this is remembering that data that we're taking from random samples follows a rough normal distribution. It's not perfectly normal, but again, that's another idea we'll circle back to in a minute. But the thing about this formula is it's only true if we have a sufficiently small sample size. Like if the sample size is too large, like say we took out of a PLNU population of 2,500 students, let's say we took 2,000 of them, right? That's almost the entire population. That sample is going to be almost exactly perfect. But what that also will mean is that the standard deviation will be really small. But basically what you can kind of remember is as long as your sample is less than about 5% of the population, like say about 100 students out of 2,500, that is a little under 5%, then it should follow this rough estimation. But even if it was larger than 5%, we know that sample is better still because of the law of large numbers. But basically, additionally, for some reason this is standard bred, this should say standard deviation, but these facts about the mean and the standard deviation of X bar are true for any population, even if it is not normally distributed. So this is the other thing I want to say. Sorry, again, my face is blocking this particular paragraph. But notice that rolling a dice is not a normal distribution, right? Because if you roll a die, you'd expect to get either a 1, a 2, a 3, or a 5, all with even probability. That distribution would be it would be exactly equal. Because let's say we rolled them 10 times, or 12 times, we would expect on average to get 2 of each. Now that's not going to happen every time, but basically it is a non-normal distribution, the expected outcome of rolling a dice. But when we look at the sample distribution of rolling dice 400 or 200 times, depending on the sample size, notice it follows a general normal distribution. And that is another key behind this idea, which is often referred to as the central limit theorem. But we'll get to that. So I'm getting a little bit ahead of myself. But let's just talk about a few details of what we call the sampling distribution. And sometimes our book refers to this as the sampling distribution of X bar, because basically the statistical meaning behind this is when we take X bar, that's the average of our sample. And that describes a particular random sample, which is a part of a larger sampling distribution, right? The sample could be different. And basically our idea is to extract information about X bar and the accuracy using the ideas of a sampling distribution. But, key things to remember is that the sampling distribution of X bar is always centered at the average, right? When we're looking at the sampling distribution, the sampling distribution always has a mean which is equal to the actual mean of that population. Now, again, we might get data points, our X bar might be over here, but the actual distribution itself is centered at this. And so it's kind of like if we're looking at this data point, which is our actual data point, the question is how far away is that from the real value of the mean? That's something we don't know. However, if we know the standard deviation, since we know it will follow a normal distribution, we could say, okay, what's the z-score of this position and figure out the likelihood of that happening. That's a key logical idea that goes into statistical inference. However, what's nice about X bar, we sometimes refer to it as an unbiased estimator of the parameter mu, because basically it's randomly, right? When we're taking a random sample to obtain our mean value, there's no bias, right? If it's from a simple random sample, the only thing that affects that outcome is random probability. Like if we're rolling 5 dice, right? We might get an average of 4.4. That's higher than the actual average, but it's not because of bias in the methodology. It's based on the element of randomness. Or we might get an average of 2.1, way lower than the actual mean of 3.5, but it's unbiased, right? It's random chances controlling whether those numbers are really high or random low. It's not caused by poor survey methodology. And so basically there is no systematic tendency to over or underestimate mu. So removing our error in, again, assuming we're removing our sampling errors, the only error that we're left with is random chance in this problem. And we can determine, what's the likelihood that this random chance happens. And then basically how close our unbiased estimator falls to the actual parameter is based on the variability in the sampling distribution. So again, lots of big words in this sentence, but going back to the example, it's kind of like if our actual data point is here, we can use the standard deviation of our sampling distribution, which we could know, to figure out how unlikely this data point would be. And the variability controls the chance of this happening, right? Because when there was a lot smaller chance to get like a value of say 2.2 to 2.6 when we had a larger sample size. There was only 8 outcomes out of 200, rather than over here we had 35 outcomes out of 400, much higher percentage. And that's all based on the variability, aka the standard deviation of the sample distribution. Again, key thing to remember, if you remember nothing else from any of these lectures, remember that the standard deviation of a sampling distribution is the actual standard deviation of the population divided by the square root of the sample size. And again, another conclusion, which is basically the same as the law of large numbers, is that the statistics calculated from large samples are less variable, aka more accurate than those from smaller samples. So essentially, larger sample size means better results, as we kind of already knew from previous ideas. Also, the sampling distribution of a sample mean, if the initial observations have a normal distribution with a particular mean and standard deviation, the SRS distribution will have a different normal distribution. Notice it has the same mean as we already kind of talked about, but the only changes in the standard deviation will be reduced from the population's distribution. Remember that population distribution refers to the actual distribution of data, whereas a sample distribution refers to taking some of those data points a lot of different times to view the different types of outcomes you could have.